Hello and welcome back to this second example of where we can apply nodal analysis to some electrical circuits. Again, as in our previous example, it's worth, if you haven't done so already, to watch our introductory video where we talk about nodal analysis and how we can set up a system of equations. We're going to jump straight in here, and so if you haven't watched that video already, it's well worth watching that video first. Here we have a second example. We've already looked at an example in a previous video, and this particular example is actually probably easier than the previous example, but I wanted to include it because it's a common source of misunderstanding. When we look at the diagram here, we might be tempted to conclude that there's a total of 4 nodes, including our 0 reference node, just like our previous example. So we have 3 unknowns, but only 3 of these nodes are numbered. We've got 0, 1 and 2. So why have we disregarded one of these nodes? Well, the answer is that our disregarded node is not really a different node at all. It's the same as node 0 because they're shorted together by just a wire. If it helps, our diagram could have been drawn like this one. Both diagrams are electrically identical, but in this case it's more obvious that there's only 3 nodes in the circuit rather than 4. So try not to be caught out by that. It's important to be careful when beginning nodal analysis to first determine the correct number of independent nodes and not just count the dots, as it were, because that can sometimes be a bit misleading. So let's carry out nodal analysis to calculate what we only have as being 2 unknown voltages, V1 and V2. Remember, this node 0 we're defining as our reference node at ground at 0 volts. So we know that the voltage here is 0. We're defining it as 0, and that leaves us with only 2 unknowns. And so firstly, defining our nodal equations. Again, we explained this method in more detail in the introductory video, but we have a current applied to this node traveling towards this node 1, and it's 3 milliamps, so 3 times 10 to the minus 3 amps. And we're setting that current as being equal in the form of Ohm's law, like I equals V over R. On the right hand side, we're going to have something in the form of V over R. We have the voltage at this node. Well, we don't know its voltage. We're going to call it V1 and V over R. So we're putting that over the resistance, and the resistance we're defining as whatever resistances in this case are connected directly to that node. And so we have 4K and 2K in this case directly connected to that node there. And so again, as in our previous examples, these are in parallel. Starting from that node, we can go this way through the 4K, or we can go this way through the 2K. And so we have 4K in parallel with 2K on the bottom there. So we have V over R, voltage over resistance. From that, we're subtracting any paths that take us to the other unknown in this circuit. The other unknown node is V2. And so are there any paths that take us directly from node 1 to node 2? Well, yes, there are. We can go directly through this resistor here, the 4K resistor. And so we must subtract V2 over 4K. In other words, we can go from node 1 to node 2 via this 4K resistor. For our second equation, we're at node 2 now. We have a current directly connected to this particular node here. We have this 5 milliamps. Again, we're expressing these equations in the form of I equals V over R. And so we're having our current on the left-hand side first of all. This 5 milliamps is directly connected to node 2, but notice that it's flowing away from node 2 or out of node 2. And so we express that by making it a negative. We have 5 milliamps or minus 5 milliamps, as it's going to be in our case. And so we have minus 5 times 10 to the minus 3 as our current here. Again, we're saying that that's equal to something in the form of V over R. Well, in our case, we have we're at node 2 now. Are there any resistances that are directly connected to node 2? Well, yes, we have this 4K and this 6K. Again, we express those as being in parallel. So we have V2 is the voltage now, V2 over 4K in parallel with 6K. And from that, we've got to subtract any paths that take us to unknown nodes, other unknown nodes. Well, we are directly connected from node 2. This equation's for node 2 now, but we're connected to node 1 via this 4K resistor. We can leave node 2 and go to node 1 via this 4K resistor, as it were. And so we have to subtract V1 over 4K. It's a good habit. We've spoken about this in previous videos, but it's a good habit to keep these terms in order: V1, V2, V3, V4, so on. And so we'll rearrange that equation so that it's in order, just like the first equation was, V1 first and V2 second. So we'll have something that looks like this. Again, we've mentioned this in a previous video as well, but why don't we subtract V0, this voltage, over 6K? We can leave node 2 and go to this node 0 via the 6K. So by the same logic, we should say minus V0 over 6K if we're subtracting these paths to other nodes. Well, we could do that. There's nothing wrong with doing that. But remember that we're defining V0 as 0. We're defining it as our reference node, as our ground node. And so V0 is 0, and so we're subtracting 0. So there's not really much point in including it in our equation in the first place. So looking back at these equations here, we have a couple of instances of parallel resistors. We have 2K in parallel with 4K here, or 2000 in parallel with 4000. And we have 4000 in parallel with 6000 here. And this is just my shorthand, this double slash notation for two resistors that are in parallel. But if we actually work those out, we'll get, in the case of 2000 in parallel with 4000, we'll get 4000 over 3. And I'm just keeping that as a rational number in fractional form because it's going to help us keep things simple later on. And we have 4000 in parallel with 6000, and that comes out as 2400. So again, I'm not rounding this 4000 over 3 here. I'm not going to convert it to a decimal. I'm going to leave it as it is, as a fraction for now, and we'll see that it'll hopefully allow us to make some simplifications in just a second. So let's return to these equations that we've set up here. And what we'll do is we'll put these parallel resistor values in where we previously had that shorthand notation. So now we have V1 over 4000 over 3 in our first equation, and we also have V2 over 2400 in our second equation here. Everything else has stayed the same there. Now remember this rearrangement. We could make a little shorthand note on the side here to say that if we have a sort of what's called a complex fraction, a fraction that includes a fraction as its denominator here, which looks a bit untidy, we could use this little rule, this little identity. If we have, let's say we have something in the form of A over B over C, then that's the same thing as CA over B. And so let's apply that logic here. We can say that V1 over 4000 over 3 is the same as 3V1 over 4000. And that looks a bit tidier now. So our two equations now look like this. Let's simplify a little bit more, because we can multiply both sides of these equations by 1000. We can multiply them by whatever we like, really, providing we do the same thing to both sides. But multiplying by 1000, we get rid of these times 10 to the minus 3 terms on the left-hand side here, and we're just left with 3 and minus 5. And you'll notice that multiplying everything else by 1000, we had 3V1 over 4000. Now it's just 3V1 over 4, and so on and so forth. Next up, let's simplify a little bit more. Hopefully you can see this first equation here now. It would be easy to multiply everything in this equation by 4, because we'll get rid of these 4 these 4's in the denominators here, and the left-hand side multiplied by 4 would just give us 12. So we can simplify that first equation quite easily. This second equation, though, on the other hand, it's not quite clear what we can multiply by, because we have this decimal here on the bottom here. We have 2.4. So what we can do here is cheat a little bit. Hopefully you'll agree that this term, I'll just write it at the side here, this term v2 over 2.4, I could write that as 1 over 2.4 times v2. They're the same thing. And if you have a scientific calculator that displays numbers in sort of a rational fractional form, if you put 1 over 2.4 or 1 divided by 2.4 into a calculator, it'll give you as a rational number 5 over 12. And so what we can say is that we have 5 over 12 v2, or 5 v2 over 12. And so now when we replace our value in the term in the equation rather with 5 v2 over 12, it becomes a little bit more obvious, hopefully, that we can multiply everything in this second equation by 12 to get whole number coefficients for all the terms in this equation. And so when we do that, remember we said we're going to multiply this whole equation, this first equation, by 4. And we've just said that we're going to multiply this second equation by 12. We will get something that looks like this. We have 12 equals 3v1 minus v2. That was multiplying the first equation by 4. And for this second equation, we're multiplying everything by 12. So we get minus 60 equals minus 3v1 plus 5v2. So hopefully you can see, by taking the time to do some of these mathematical operations here, we have transformed what was a fairly nasty pair of equations to begin with into something that looks a lot more manageable. And it's a good idea to try and simplify in this manner as much as you can before then starting to try and solve. Let's get on to solving. We can use some of the same approaches that we mentioned in previous videos when we converted to matrix form, and we used things like Cramer's rule or the inverse matrix or Gaussian elimination, those kinds of things. But in this case, we only have 2 equations and 2 unknowns. We can hopefully just solve using simultaneous equations. And in this case, let's add both of our equations together, because what we can see here is that the v1 term is 3v1 in the first equation, and we have minus 3v1 in the second equation. And so they're going to cancel out nicely. If you don't have something like that, then you can always multiply one of these equations to make that so. But in this case, it's already set up quite nicely for us. These two are going to cancel when we add these 2 equations together. And so when we add the left-hand side, 12 plus minus 60, we end up with minus 48. When we add the right-hand sides, these v1 terms are going to cancel. We're left with minus v2 plus 5v2, and that gives us 4v2. And so we have minus 48 equals 4v2. And that means that v2 is going to be minus 12, dividing both sides by 4 there. Now that we know v2, we can substitute that into either of these first 2 equations. Let's just take the first one. It doesn't really matter, but it allows us to find v1. And so now, rather than writing 12 equals 3v1 minus v2, I'm going to write 12 equals 3v1 minus 12, because I know the value of v2 now. And what we can do then is we can, well, first of all, this minus, we can say that that's a plus, so we have 12 equals 3v1 plus 12. Subtracting 12 from both sides is 0, and 3v1 is 0, which means that v1 must be equal to 0 as well. So we've now solved these equations. We've found that v1 is equal to 0 volts, and v2 is equal to minus 12 volts. And we've done that just by using some simple simultaneous equations in this case.